How's it going, Algebra 1? It's Mr. Knight here, and this is our final lesson of Unit 6 before we start getting ready for our test. We have looked at monomials quite a bit. We've looked at the monomial rules with their exponents, when we multiply, divide, negative exponents, that sort of thing. And this is the last thing when it comes to exponents. And it's very different than what we've done, but it's very applicable to real life and kind of using it. And you can actually use this in real life to help you when it comes to money. When we're talking about exponential growth and decay. So if you think about it, there's a lot of things that change, but not at a fixed amount. For example, if you're thinking about like a population of people moving into Kingman, they're not just coming at 500 people every single day, right? Sometimes it's this much, sometimes it's this much. And it gradually increases over time. There's more and more people that are moving here to Kingman than they were just 20 years ago. Okay, and we can actually measure that growth of population with an exponential growth equation that we have right here. And so we're going to kind of talk about what each of these variables are, this a, this r, this t, and try to do some problems and actually use this guy because it's more or less a tool at our disposal. So exponential growth, it occurs when a quantity increases by the same rate over time. And we have these three variables in this problem. The A is going to be our starting amount. It could be money. It could be population. It could be radioactivity. It could be a lot of different things. It's just our starting amount, whatever we're measuring, right? The R is our rate, right? So it increases by the same rate over time. That's our R right there. Okay, that's our rate. Now, most of the time, they're going to give your rate as a percentage, but what we want this to be in is in a decimal. Okay, so if you want to go from percent to decimal, we'll see how you do that. Again, review, we did that way back when, but I'll show you again how we do that. And then T, that's our over time. So it increases by the same rate over a fixed amount of time. And that time, it can be measured in seconds, years, days. Usually, they're going to measure it in years for these problems. So I'm going to put years just for right now, okay? And let's look at a couple problems. So I want to look at number 2 to start and kind of get you an idea how these problems go. So the cost of tuition at a college is $12,000, and it's increasing at a rate of 6% every single year. Write an exponential growth function, so using this guy, to model the situation. Then find the tuition costs after 4 years. So a lot of you guys are going to go to college after high school, and so this is kind of a good idea to see how this problem would work, right? So tuition's expensive. The cost of tuition at this college was $12,000. That's going to be our starting amount. That's our A right there. Okay, and it's increasing at a rate of 6%. Now, like I said, it's going to give you the rate as a percentage, but we want the rate as a decimal. So, to do this, we take our 6% and we are just going to divide by 100. And if you do that in your calculator, you'll get 0.06 is the rate we want to use. And then finally, T, our time, that's after 4 years. Okay, so kind of putting all this together, we're going to use this function. The y equals, the a is now 12,000, parentheses 1 plus our r, which is 0.06, and it's raised to the t power, or the 4th power in this case. And that's all there is to it. So that's part of it, is write an exponential growth function to model this equation. There it is. Okay. Then it wants us to find the tuition costs after 4 years. Use a calculator. Do not try to do this in your head. It will be, I don't want to say impossible, but I think pigs growing wings is more likely than you doing this in your head. It's just really hard. So use a calculator. Now, when you set this guy up, you want to set it up pretty specific and use PEMDAS, right? Because if I just I can type in the whole thing, and that's fine, but you need to be careful how you type it in. So I'm going to type in my 12,000, put my parentheses, my 1 plus 0.06, which is 1 plus 0.06. Close that parentheses off, and then we're going to raise it to the 4th power just like this. And we end up getting a number like that. Now we're talking about tuition, we're talking about money, so we do want to round off to the nearest cent, the 100th place. So we could say that y is equal to $15,149.72. And that's after about 4 years, okay? So after 4 years, if the tuition keeps increasing, this is what we can expect it to be using this model function right there. So if you're a freshman right now and you notice, oh, a school's tuition rate is this, and I know it's changing at this rate, you can predict by the time you get out of high school in 4 years how much that tuition is going to be at that point in time. Okay? So it's useful in that sense. It's also good for populations like number 3. So the number of student athletes at a local high school is 300 and is increasing at a rate of 8% per year. Write the exponential growth function to model it, then find the number of student athletes after 5 years. So what I did was I just underlined what I thought were important pieces of this problem. What I did was I highlighted my starting amount of local high school student athletes. That's my A right there. Okay. I also underlined how much it was increasing by, the rate of 8%. Once again, I'm taking that 8%, I'm dividing by 100, and so I'm going to get 0.08, and then my t is after 5 years. Okay, so putting it all together in that equation up here, it's y equals 300, 1 plus 0.08 to the 5th power. Just like that. And once again, use your calculator to figure out what the number of student athletes will be after 5 years. Pull this guy out again, and we're going to type it in. So let's see. We're starting out with 300. It's increasing by a rate of 0.08 every single year. Oops, not 0.0. Did I type that in right? Good. And then it's going to be after 5 years. We're predicting how many student athletes are we going to have? Apparently 440.798. Now, you can't have 0.798 of an athlete. You just can't. That's kind of weird. So we're going to round off to the nearest whole number. So we're going to round up to 441 about, and you could use this to show approximately 441 student athletes. Which is quite a jump in 5 years. We added 141 student athletes. That's pretty crazy. Okay, we can actually do that at Lee Williams too. If we found out how many student athletes we had and got an idea of how much our population's increasing, then we could determine in 10 years how many student athletes we should get. Same idea. Okay. Let's look at number 5. Once again, we're talking about population again, right? We're saying the population of a small town is 1,600. That is small. Kingman's like 35,000. That's pretty tiny. Population is 1,600. It's increasing at a rate of 3% every year. Write an exponential function. Then find the population of the town after 10 years. So there's my T. There's my R. There's my A. I'm just going to put it all together. Okay. So Y is going to be equal to, my A is 1,600. 1 plus my rate. Now, this is 3%. I need it as a decimal, so I will divide it by 100. I will get 0.03. So 1 plus 0.03 raised to the 10th power. And there we go. There's my exponential function to model the situation. I'm throwing it into the calculator once again. And our label is going to be, I guess, number of citizens, I guess. So it's like, 2,000 citizens. Let's see what it turns out it is. Okay, 1,600, 1 plus 0.03, raised to the 10th power. Whoa, 2,150.2. Again, we're talking about people, so we do not want to include the 0.2. We're just going to round it off to that and just say people or citizens, either one. It's good, okay? There we go. So a lot of this boils down to figuring out what your A, R, and T are, and then putting them into this guy. That's really it. So the word problems will be the toughest part because you're trying to just figure out what each thing is. Your A is your starting amount, whatever that starting amount is. R is the rate, so look out for a percentage. T is your time, so look it for a certain amount of years. Okay. Let's go ahead. Let's flip our page. Let's do a couple examples with exponential decay. If something can grow, it can obviously also decrease. And if you look at this decay, compare that to the exponential growth, it's pretty much the same exact thing. The only difference is this guy has a minus sign. This guy's a plus. Okay? So this was for your growth, which we saw on the first page. This is your decay. And that's really the only difference. Everything else is the same. The A is still your starting amount. The R is still your rate. T is still your time. Usually in years. Okay? And it occurs when a quantity decreases over a certain amount of time. Whoa, what happened to that A? It turned into a G. That's weird. Something like that. Let's look at number 7. And we'll look at number 8, and we will conclude the video lesson, okay? So, the population of a town is decreasing at a rate of 1% every single year. In 2000, there were 1,300 people back in 2000. Write an exponential decay function to model this situation, then find the population in 2008. Okay, so it didn't say for our time, it didn't give us like, hey, here's the amount of years. Well, it's saying from 2000 to 2008, you know, how is the population going to change? So our years, our T is 8 years. Okay? Our rate is at 1%. It's decreasing, right? But again, the decreasing part will take care of itself. The rate is 1% or 0.01 when you divide by 100. And then the A, our starting amount, that was however many we had in 2000, which was 1,300 people. And now we can put all this together. Okay? So our equation is y equals A is 1,300. 1 minus 0.01 was our R, raised to the 8th power. And let's find out how small this town got after 8 years. 1,300. 1 minus, can't forget the minus now, 0.01 raised to the 8th power. And we should end up with a number that is smaller than our starting amount because we're decreasing. And it turns out we do. We get about, well, 1199.5, so we can round up to 1,200 people. 1,200 people. All right, so we lost 100 people in 8 years in this town, which actually, it's quite a lot, actually, if you think about, like, the scale of the town. That's like, what is that? That's a 13th of their population they lost. Wow. Okay, and number 8, the value of a car. This is important, too, because you guys are going to be driving pretty soon. You're going to have to buy a car at some point in your life. You might want to get an idea how this works, right? The value of a car is $18,000. Okay, so that's our starting amount. And it's depreciating, which means it's decreasing in value. It's depreciating at a rate of 12% per year. There's our R. Write an exponential function, then find the value of the car after 10 years. There's our T right there, okay? So, putting this all together, I know I'm going to use the same equation. Y equals A is 18,000. We have 1 minus our rate, 12%. Divide by 100, you get 0.12 to the 10th power. And let's just see how much this car depreciated by. Again, I type it in exactly as I see it. 1 minus 0.12 raised to the 10th power. Again, that number should be smaller than the starting amount, and it is way, way smaller. Y is equal to $5,013. And what's our cents? Well, we got 1 cent, but we have a 7 right here, so raise this up to 2 cents, so 0.02 cents. There we go. And those guys are done. Thank you for watching. We will do some practice on this on Wednesday and Thursday. See you soon.